Hello everyone. So today we're going to do something a little different. We're going to look for a vulnerability in a piece of software, in this case SLMail, and we're going to use that to develop an exploit. So we've been using all these exploits throughout the course of the trimester, and we've been using them a little bit as a black box, so we haven't really understood how they work. So today we're going to try and figure out how people find these exploits and what's going on under the hood. There's not going to be an exhaustive look at that by any means, but it's enough to sort of get the general idea. So normally when I make these videos, I really only do it up to the level of the pass task, and then you all have to do a lot of research to do the distinction task. This time I'm going to record all the way up through the distinction task because I think this is pretty challenging if you haven't done this type of programming before. So I want to make sure everyone can really experience the whole thing. Alright, so as usual, I've got my XP on internal network, got my Kali on the internal network, and I've got my pfSense running things. Alright, so I've got this SLMail. It's got an SLMail configuration. You click control, it's going to bring this up. Every time we crash the program, which we're going to do a lot, you're going to need to click restart. Alright, we're going to use this debugger to look at what's happening inside the program when we attack it. That's how we're going to find out what needs to happen. Alright, so if you've attached the program to the debugger before, we'll offer to start up a new copy. If you do that, Windows will complain because you're not supposed to start up services directly like this. So don't do that. You have to attach directly to the process. So here's my mail program. So go ahead and click attach. And the first time you connect, you're going to hit a default breakpoint. So you're going to want to start the program again. So now the program is running. So let's go back to our Kali. So I've written a few Python scripts here, to attack the program. And I like to run them inside IPython. You can run them, however you like, but this is my preferred way of doing it. So first of all, I'm going to just try and connect to the program. So I'm going to try and log in. Well, I'm not going to be able to log in because it's not a real password, but I am going to connect to the server. So pretty much create a connection, receive the data, send my username, send my password, and see what they say. So if I want to see what they said, I could always print data. And here it said error unable to lock mailbox because I didn't have the right password. Alright, so it's well known in this program that there's a buffer overflow we can get inside this password here. So what we're going to do is we're going to fuzz this program. So what does fuzzing mean? We're going to send a bunch of incorrect input to one of the things the program is expecting and see if we can get some errors. So how am I going to fuzz the program? I'm going to send a buffer of a password of all A's, and every time I successfully don't crash the program, I'm going to increase the size of the buffer by 200 A's until I figure out how big the buffer has to be to crash the program. So that's going to be the basic information we need. How much data do I have to send for the program to die? And then when I get a crash, I'm going to go ahead and look in the debugger and see what the issue is. So while we're fuzzing, I want to talk about the strategy that we're going to do here. So we're going to try and overwrite two things. We're going to try and overwrite our stack, and we're going to talk in the lecture more about what the stack is. And we're going to try and overwrite our instruction pointer. So the register that contains what instruction we're going to do next. So there's two strategies. So we're going to try and overwrite the stack with our own program, and then we're going to try and put an instruction that is going to jump into the stack or into our code. So we need to figure out how to do those two things. Chug. And actually, it's going to be just a little bit more complicated than that. While we're doing this, I'll elaborate. So, in fact, the register, the EIP, has an address to the next instruction. It doesn't have the next instruction we're going to actually run. So we're going to have to find a place in memory that has the instruction that jumps onto the stack for us. So technically, we're doing two things. We're going to look in our code, find out where there's an instruction jump to the stack. We're going to overwrite our stack with our code, and then we're going to put inside the instruction register the address of the next instruction that we want, which is going to be wherever that jump is. All right, so it's been stuck here for 2,700 bytes for a while. That probably means it crashed. So I go back to my XB, and in fact, I did get a crash. And here we can see inside this register, which is associated with the stack, that I've overwritten it with 414141, and here's my instruction pointer, 41414141. So we did manage to overwrite that. So what we want to do now is figure out where in this 2,700 bytes ends up inside this instruction pointer. So let me, because remember, we want to make this address to be a specific place in our program that has a specific instruction that we want. So we need to figure out where inside this list of ones we need to change to make it end up here. All right, so I'm going to close this, and I'm going to want to restart our service. Chug. Let's go ahead and reattach. I must attach to the wrong thing there. Alright, and again, we're in a breakpoint, so we want to continue the program. So now we're running. Alright. So instead of sending a whole bunch of ones, we're going to send basically a random pattern, and we're going to see what part of the random pattern ends up in the instruction pointer in the EIP, and that's what wherever that pattern is in our sort of random list, that's the part of our sort of 2,000 bytes that we need to send over to overwrite the instruction pointer. All right, so it turns out that Metasploit has a nice program which will make this random pattern for us. User share Metasploit framework tools exploit pattern create Ruby RB, and then you have to tell it how big you want it should be. We're sending 2,000 bytes over, 2,700 bytes over. All right, so here's my gigantic random pattern. I copied this into my buffer here. I'll just copy this over to IPython now. Let's double check that it worked. Alright, it did. So basically my code here is just doing the same thing, logging in as locally, then sending over this random pattern, and we're going to go see where in the pattern we overwrote the instruction pointer. Alright, so let's go back to our thing here. And you see we got a crash again, as we kind of expected. And here's our instruction pointer. So this is part of the pattern that ended up inside our instruction pointer register. So let's go back here, and it turns out that there's a program in Metasploit that will tell us where in our code, where in our pattern, the string occurs. And that's at the 2,606 byte. So what is our exploit going to look like? It's always going to be 2,700 bytes. The first 2,600 are going to be just A's because that doesn't matter. Then the next 4 bytes are going to be whatever we want to end up in the instruction pointer. So the instruction pointer register. So it's going to be an address that contains an instruction that we want to execute. So that's going to be 4 bytes. So we'll just put 4 B's for the moment, and then the rest of it is going to be our code that we want to execute. All right. So unfortunately, that's not all there is to it. It turns out that a lot of times when you're sending over a bunch of characters, the program is going to modify some characters in some way because it's looking at that input and it's doing some processing on it. So we're going to send over a whole list of characters, we're going to send over all the ASCII values, and we're going to see which ones get messed up. And then when we encode our exploit, we're going to make sure that our encoder doesn't use those particular ASCII values. All right. So again, got to stop our program. Should be getting used to this by now. Restart the service. Immunity debugger. Attach. Go to SLMail. And again, you hit a breakpoint, so go ahead and run. Alright, so I go back to my code here. Excuse me. So I'm going to send over all these characters. And again, so the first 2,606 bytes, just A's, we don't care about those. Then we're going to send over 4 bytes that go in our EIP, and then we're going to send over the bad characters. Alright, so that's what's going to be in our message. Alright, so if I go back to my debugger again. Alright, so here is stuff I overwrote. So first of all, we can double check that we got what we wanted here. We wanted 4 bytes to go in our instruction pointer. In fact, they do. 42 is the ASCII value for B. We see that here. We send over all these A's, and they're in memory. We overwrote instruction pointer, and now here's what's in the rest of the stack. So we send over 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we would expect to see the hexadecimal value for 10 here. That didn't make it, so that's a bad character. So it turns out there's 3 bad characters. I'm not going to go through finding all 3. I'll just show them at the end here. But that would be the process, as you send them all over, and then you see which ones you can't use. All right, so I'm going to close this again. Stop this. So now we know what our bad characters are. We know we know what our bad characters are. We know how to fill something into the instruction pointer. So we now need to find out exactly what should go into our instruction pointer. So again, the instruction pointer is a place in memory that tells you where to go next, right? Whoops, sorry. So let's go ahead and attach here. And go ahead and attach to SLMail. Alright. So now I need to find my notes here. Excuse me just 1 minute. Alright, so we're going to use this module Mona. Just make sure I'm not skipping any steps here. Modules. So this is going to help us find a place in memory that has the particular instruction that we want. Alright, so what are we looking at here? We are looking for, so first of all, you see up here, these are certain security things. So for example, this address space layout randomization. We want something that doesn't have that turned on, right? Because we're going to put address in memory. And if these addresses, we're going to put an address into our instruction pointer register. If these addresses are randomized, then that's not really going to help us too much. So I'm going to look down here and find one that's got all these set defaults. And let's see here. There's one in particular I want to use. SLMFC. False, 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 false. So that is good. It is an OS DLL. That doesn't matter. It's got all these security modules turned off. So what we want is we want to use it to find a particular instruction. So the instruction we're looking for is jump, and then we want it to jump to the SP, the stack pointer. So that's basically where we have all our code is going to end up. And if you look in the table, that's just these are just the hex values of that instruction. All right, so we have to say what DLL we're looking in. All right, so there's a bunch of places in here we can use. Doesn't really matter which one we use. Just take this guy, I guess. All right. So now start our server. So that's what we're going to put inside the EIB register. All right, so let me go ahead and attach. Whoops. Don't really want these, so let me go ahead and tile. Don't want that either. Alright, much nicer. Alright, so now let's go ahead and create our exploit. So we're going to use our old friend MSF Venom. I'm going to use a reverse shell. This time I'm not using an interpreter. I have to say what my IP address is. It should be 101. To say what my port is, I always like 1337. I have to say how I'm going to send it over. I'm going to send it over in Python. And then I have to say the 3 bad characters I found. So the 00, this is the null terminator for C string, so it's not a surprise it's a bad character. These are the other ones I found just by sending over the bad characters here. And then this is the reverse shell I'm going to send over. Alright, so here are the bytes of my reverse shell. You can just copy them into this string here. Alright, so this is the address I previously found. So this is where I've got my jump command. So this is the address I have my jump command at. So that's going to end up in my EIP, my instruction pointer. And then my buffer. And then I've got some no-ops. Why do I send over some no-ops? Is because if I didn't have the no-ops, this together wouldn't be equal to 2,700 bytes, which we know is what crashes the server. So we're going to send over the whole thing. So we're going to have to add some padding, and the best padding is just no-ops, things that do nothing. Alright. So let me copy my buffer over first. Alright, so now I need to set up a listening post. So using netcat as we normally do. And now I'm sending over all my stuff. And actually, I don't really want to use the debugger here, right? I want it to run normally. So let me go ahead and start that. Because the debugger may interfere with my code executing, right? Alright, and then immediately you see I get a shell. And now everything I run over here runs on my victim. Alright, so that's the whole sort of process of looking for an exploit. We did some fuzzing. We overwrote EIP with a particular address that had a jump instruction, and that jump instruction jumped to a bunch of code that we put onto the stack. Alright, very good. So obviously there's some details here that we kind of glossed over. If you want to hear about the technical details, please come to the lecture and we can discuss it. Otherwise, as always, send me your questions. Shoot me an email or get me on Discord or Cloud Deacon, and happy hacking.